Hi everyone, welcome to goclasses. So this is part 2 of first order logic gate PYQ. In the part 1 we have done a lot of gate questions of first order logic, and the remaining questions we will do in this part. Now we have seen the first type of question we have seen, which are the conversion of first order logic to English and the conversion of English statement to first order logic. So this type of question we have already seen all the gate questions of this type, all the gate questions of type 1. So this is already done in the part 1. Okay, all these questions in the part 1 we have done in the part 1. Also, the second type of question which are related to negation of quantifier, this type of questions also we have done in the part 1. So these questions also you can watch. And the third type of question type 3, that is nested quantifier, these questions also we have done in the part 1. Okay, so this part 1 you can watch on the Go Classes YouTube channel. Now let's see the part 4, that is questions related to validity, satisfiability, tautology in first order logic. Okay, so these are the interesting questions, and a lot of questions are coming in the GATE exam from this type, from this topic, like related to validity, related to satisfiability. A lot of questions are in the GATE exam. Okay, these are very important, so that is the reason I have put 5-star here. 5-star means that this topic is very important for the GATE exam point of view. A lot of questions are coming in the GATE exam from this topic. Okay, now what I am going to do, I will tell you how to solve all these questions, the method I will tell you, and you can solve the questions with me. You don't have to watch the video like a movie. You can take your copy pen and you can solve the questions. I am solving the question, you can solve the questions with me. So let's start. First of all, the concept to solve these questions, let me revise that concept. Then we will solve all these questions. First of all, let me tell you what is a model. First of all, let me tell you what is interpretation. What is the concept of interpretation? Interpretation of a first order logic, what is that? So this concept, like what do we say when we say that first order logic interpretation? So this interpretation of first order logic, it simply means that all the information you need to find out the truth value of a first order logic expression. Okay, interpretation means, so basically this interpretation, it simply means give me a domain plus in that domain you give me the truth value of basically in this domain you give me a domain, and what you do, you give me truth value of every predicate. Okay, so what you do for all elements, so basically tell me the truth value of all predicates, or I can say basically you give me domain plus predicate. So these two things you give, domain plus predicate. Okay, so this is called interpretation. Now let me take example so that you can understand this. For example, consider one expression I am giving you, this expression like for all x px. Can you tell me is this true or false? Tell me, if I ask you is this true or false, tell me. The expression is given to you as which is for all x px. Then if I ask you is this true or false, what you will ask me? You will ask me is basically is s true or false? What is this? Truth value of s. You find the truth value of s. So what you will say? You will ask me what is the domain and what is px, right? So you will ask me what is the domain and you will ask me what is px. Agree? So now I have to give you this domain, I have to give you this predicate. So if I want this, then what I need? I need domain. I need this domain. I also need the information of predicate. Okay, these two things are needed. I need these two things, correct? Now, let me give you these two things. That is an interpretation. So once I give you these two things, if I give you, that will be called an interpretation. Okay, is this clear? Is this clear to everyone? So if I give you these two things, then that will be called interpretation. This is called interpretation. So like, let me give you. So for this statement, this is your expression for all x px. For this, let me give you interpretation 1. Let me give you interpretation 1. Let me call it I1. So what is this interpretation 1? In this interpretation 1, the domain I am giving you, the domain is, let's assume, set of natural number. This is the domain, 1, 2, 3 and so on. This is the set of natural number. And the predicate that I am giving you, the predicate is, let me assume, the predicate is prime. x is prime. Okay, this is the predicate. Let's assume px is, or I can say x is even. Now you tell me, in this interpretation, what is the truth value? Now can you tell me the truth value of s? Now can you find out the truth value of s? So the truth value of s in this interpretation, in this I1, what is the truth value of s? Then you can clearly say that is false. Yes or no? In this interpretation, s is false because statement s, this expression s is saying that for every element in the domain, px is true. Okay? For every element in the domain, px is true. But you can see that for every element, x is not even. So this is not true that for every element, this px is not true. So I can say this si1, that this will be false. Okay? So in this interpretation, this statement is false. Now, this type of interpretation, because s is false in this interpretation, so for s, this I1 is a co-model. Okay? For s, this I1 is a co-model. This I1, this is a co-model because s is false in this interpretation. Now let's see the next. Let me give you another interpretation, interpretation number 2, and that is like this. What I do? Let's assume x is greater than equal to 0. Now you tell me. Now you can see that this s in the interpretation 2, this is true. It is true. So because this s is true, because for every element in the domain, for every element you can see this p is true. This statement is true for every element in the domain. So what we will say? In this situation, I will say that this I2 is a model for S. Is model for S. Okay, so the definition, did you understand? Please tell me. Did you understand the definition of interpretation? What is interpretation? Interpretation simply means that you give me all the information so that I can find out the truth value of a expression. Interpretation means basically give me all the information. Interpretation of first order logic. Okay, in the simple words, I can say give me domain, give me this domain, and give me this predicate. Give me this predicate. Give me these two things. Okay, give me domain, give me this predicate. This will be called interpretation. Now remember, if you have some expression s, and let's assume this expression s in interpretation I, this is true. Okay, so you can see, let's assume this expression s in interpretation I, in interpretation I1, expression s in interpretation I1 is true. Then this I1 will be called model for s. What is this I1? This is called model for s. Okay, and the same thing, if this s is false, okay, in this interpretation, then this or I can say I2, in the interpretation I2, if this s is false, then that interpretation will be called co-model. Okay, we will call it co-model for s. Please tell me, did you understand this concept? The model concept, the co-model concept. So these two concepts, did you understand? Now, let me take example. Consider this another example, like let me give you s, which is there exists x, sx. Okay, let's assume this is the sx. Now, in this for this, so this is your expression. Or I can write it px, or maybe whatever, like I can write it ax. Now you tell me, in this situation, if I give you what is the domain, is that enough? Is that enough if I give you the domain? Like for example, if I give you the domain as 1, 2, 3, is that enough? Let me know. Is that enough? This information is not enough to find out the truth value of s. Yes or no? This is, you can clearly see this is not enough. You can clearly see this is not enough to find out truth value of expression s. So definitely this is not a model. I need, for every value in this domain, I also need the predicate value, correct? So what I need, you can see that if I give you this value, like if I give you that a1 is true, let me give you that a2 is true, and let me give you a3 is false. If I give you this, now you tell me, now can I say this is interpretation? Can I say this is interpretation? Can I say this is interpretation? Yes, this is interpretation for s, right? So in this situation, I can say that this is an interpretation. So I can call it interpretation I1. Now you tell me, in this interpretation, this s is what? S in this interpretation, is this true or false? in this interpretation, this expression s, is this true or false? So this expression is saying that there exists some element in the domain for which a is true. So yes, there exists some element in the domain for this element a is true. So I can say in this interpretation s is true. So this interpretation will be called what? So this I1 is called what? So this I1 is because this sorry, in this interpretation s is true. So this I1 is model for s. Okay, this I1, this is a model for s, right? This is a model for s. Now you tell me what will happen if I give you this interpretation. If I give you false, false, I give you another interpretation, that is interpretation number 2. Now you tell me, in this interpretation, what is the truth value of s? What is the truth value of this expression? This expression will be clearly false. So I can say this I1, this is co-model for s. Okay, sorry, this I2, remember this I2 is co-model for s. This interpretation is co-model for s. Is co-model for s. A co-model of s. Is this clear? See, very simple topic, very simple questions. Now let me give you this. Ax implies bx. Can you give me some co-model for s? Suggest some co-model for s. Can you give me? Give a co-model for s. Can you give a co-model for s? Tell me. For this expression s, can you give a co-model? Can you give this? Give a co-model for s. Co-model means you have to make it true. This s, you have to make this false. This s must be false. So for every element, this must be false, right? If you want to make this s false, this expression s, this is the expression s. If you want to make it false, then for every element in the domain, you have to make it false. Okay, for every element in the domain, this must be false. So for every element in the domain, this must be true, this must be false, right? So the co-model that you can give me, you can very easily give me like this. So you can say that domain, for example, you can say domain is set of integers. Okay, this is the domain. And you can say there's ax. This ax, you can say x square is greater than 0, greater than equal to 0. Okay, this is ax. And this bx, you can say x is even. Now you can clearly see, so if I do this, for every element, this must be false. So I can say this x square is less than 0. Now you can see that this will work as co-model. This will work as co-model because whatever element you take, this is definitely co-model. So this interpretation, this is the interpretation, remember. This interpretation I1, and this interpretation I1 is co-model for s. So this is a co-model for s. Is this clear? So this is how you can give a co-model. Is this clear? Sumant, Ratul, let me know. So you can see that if I give you this domain, and now you can notice for every element what will happen. For every element, this will be false. Whatever element you take, this will be false. So there is no element for which this is true. So this expression s will become false. So this is a co-model for I1. Of course, you can give another co-model. You can give this co-model. For example, you can give a domain like this. Domain you can give ABC. This domain you can give. And what you can say that, okay, AA is true, AB is true, AC is true. Okay, so these things are true. And what you can say that, okay, BA is false, BB is false, and BC is false. Now this also will work as a co-model. This is also a co-model. This is a co-model for S. So this is also a co-model because in this interpretation also, so you can notice this is an interpretation. So in this interpretation also, what will happen? Let's call it interpretation I. For this interpretation also, what will happen? The S in I, this will be false. So you can see this is a co-model for S. Okay, clear? So like this you can do. Now, can you give me a model for S? If I ask you, can you give me a model for S? Simple question. Can you give me a model for S? So model means you want to make this S true. Can you make this S true? This S, can you make it true? Yes, you can make it true. Very easily you can make it true. All you have to do, for some element, you have to make this true. For some element, this ax imply bx must be true. So what you can do, you can take set of natural number, and this ax you can make it like x is even. That's it. This is enough. This is enough. Of course, I can give you bx. Bx can be anything. For example, bx can be like x is prime. Okay. Now you can see that in this situation, what will happen? In this situation, what will happen? This for this interpretation, this s will be true. So you can clearly see that this is a model for s. This interpretation is a model for s. Okay, clear? So very simple. Like this you can do. For some element, you can make either you can make this a false, or for some element you can make this b true. Okay, so this is all you have to do. So very easily you can see that this is a model for s. So I hope all these points are clear to everyone. Now this is a summary actually. This is just a revision, because all these topics, all these concepts we have already seen in our Go Classes Discrete Mathematics course, which is freely available for all the students. You can watch it. Okay, so this is the concept of model, co-model. Now what is valid? If you have first order logic expression, what is this valid? When I can say valid, validity of first order logic expression, So if you have a first order logic expression, when can you say it is valid? So let's assume you have this is a first order logic expression. Valid means always true. Valid means, okay, s is valid. It simply means it is always true. If and only if s is always true. What that means? That means that there is no co-model for s, or I can say, you can see, no co-model for s. I can say s is valid. S is valid if and only if no co-model for s. No co-model for s. You cannot create any co-model for s. Or I can say s is valid. I can say s is valid if and only if every interpretation is model. I can say that every interpretation, whatever interpretation you take, okay, whatever you do, whatever interpretation you take, every interpretation is a model. Every interpretation is a model for s. So this is called validity of first order logic expression. Okay, so is this clear? So when can I say valid? Valid means always true. Expression is valid. Valid means it is always true. There is no co-model, or I can say that every interpretation is a model. Every interpretation is a model. Everything is a model. Whatever interpretation you take, that is a model. What is the definition of satisfiability? What is the definition of satisfiability? Satisfiability. What is the definition of that? Satisfiability of first order logic. So when can I say S is satisfiable? In which situation I can say this expression S is satisfiable? So this is satisfiable if it is at least one model. S is possible to be true. S is possible to be true. You can make S as possible. Okay, S is possible to be true. Means there exists a model. Okay, there exists a model for S. Okay, it means some interpretation is a model for S. Some interpretation, remember, some interpretation is model for S. Okay, there is a model. There exists a model. Some interpretation you can give, you can make it true. You can make it true. That is satisfiability of first order logic expression. Okay, very simple. So these are the points. Now you can see invalid. When can I say invalid? In which situation you can say invalid? Like when can you say invalid? When can you say that expression is invalid? In which situation you can say an expression is invalid? Invalid means you can make it false. Okay, you can make it false. Invalid means S is possible to be false. S is possible to be false. You can make it false, because remember, valid means always true. Okay, valid means always true. So invalid means it is possible to be false. You can make it false. It means there is some co-model. It means some co-model for S. There is some co-model for S. So this is the idea. I can say some interpretation is co-model for S. Okay, some interpretation, there is some interpretation, and that interpretation is co-model for S. So you can make it false. That is your invalid. Like, let's take example. Consider this expression as, like, I give for all x px. Okay, for all x px, for every x px is true. Then can I say for someone px is true? Can I say this? For everyone px is true. For everyone p is true. Then can I say for someone p will be true? Can I say? Can I say that for everyone p is true? If for everyone p is true, then can I say for someone p will be true? The answer is of course. So this S is actually valid, right? So this is a valid expression. This expression that you have, this expression is valid because this is always true. This expression is valid. You can easily see this. What you can say, you can easily see this, that this is always true. This expression is always true. Now, one thing I want to tell you, when you have empty domain, then what will be S? Ratul, when you have empty domain, then it will be false. But remember, never take empty domain unless explicitly mentioned. This I have told you in the previous lectures also. I have told you this many times. Never, never. This is a note. Few things you should note. Okay, there are two things. One is never take empty domain. First order logic domain is always non-empty. Is always non-empty. Okay, this domain is always non-empty, remember. This domain is always non-empty unless explicitly stated. Unless they explicitly state. Unless explicitly stated otherwise. Okay, so unless they explicitly state otherwise, like if they say that, if the question says that domain is empty, then domain must be empty. But remember this, otherwise the first order domain is always empty. And the second point, by default all the variables have the same domain. Okay, this is also another point, that by default all variables in a first order logic expression refer to same domain. Again, if nothing is given to you, then all the variables in a first order logic expression, they refer to the same domain. Okay, so these are the 2 points that you have to understand. Now let's see the next. So you can see this expression is always true. But how can we prove it? Like, when logically you can think, logically that if for everyone p is true, then for someone p is true, of course. So logically you can think, this is intuitive. Okay, this is an intuitive argument that for everyone p is true, then definitely for someone p must be true. Okay, and tell me one thing, this x and this x, do they have anything to do with each other? Remember, they are completely independent x. They are different x. They are independent. Remember, these are different. Okay, so these are different and they have nothing to do with each other because they are in the different scope. So they have nothing to do with each other. So this also point. So you can see that this is the this is the domain of this variable x, and this is the domain of this variable x. Or I can say, sorry, this is the scope of this variable x, and this is the scope of this variable x. They are in the different scope. So they have nothing to do with each other. This expression is the same as this expression. For all x px implies there exists y pi. If you are confused, you can write like this. These expressions are basically same. Okay, these two are same expression. They have these two variables, this variable x and this variable x, they have nothing to do with each other because they are in that separate scope. This is one scope, this is another scope. For this universal quantifier, this is the scope. Okay, this is the scope of this universal quantifier, and this is the scope of this existential quantifier. So remember, these two statements are exactly same. Okay, so these two x, they have nothing to do with each other. Now let's see the next point. How can you prove if I give you implication statement? Whenever you have implication statement, then if you want to check validity or not, then what you can do? Okay, so now let's see. So what I'm saying, very simple point, I'm saying that whenever you have this type, this is a note that validity of implication statement. Validity of implication statement. How to do that? Implication expressions. So if there is an implication expression, how to check the validity? Whenever you have implication expression, for example, if you have some expression like A implies B, okay, this is your expression. There is something called A, this implies B, this is the expression. Now check if it is valid or not. What is the best way? What is the best way to check validity of this expression? Let's call it this expression S. Then remember what you need to do to check if S is valid or not. To check if S is valid or not. If this S is valid, valid means always true. Okay, if this S is valid or not, then what you will do? Try to make this S false. Okay, try your best. Try your best to make S false. To make S false. Okay, so what you need to do? Remember, you need to try your best to make S false. If you can, then it will be invalid. Correct? Okay, try your best to make S false. If you can, I can say, if you can, then it S will be invalid. Okay, in this situation, I can say if you can make it false, then S will be invalid. And if you prove that you can't, okay, if you never, okay, so, sorry, so I can say if you can't, if S is never false, if you can prove that S is never false, then in this situation I will say S is valid. In this situation you will say S is valid. Okay, so again I am telling you that whenever you have this implication statement, then what to do? Whenever you have this implication statement, what to do if you want to prove whether it is valid or not? Let me tell you the best way. The best way is what you do? You do this. Make A true and then try to make B false. So this is the best way. See that is it possible? Okay, just see, is it possible? Can you make A true and B false? Can you make this? Is this possible? If this is possible, if you can do this, if possible, then S invalid. If you can do this, then S is invalid. Remember, if it is possible, then S is invalid. If impossible, if this is not possible, if this is impossible, then S valid. Okay, very simple. This is the best way. All you have to do. So all you have to do is basically just make this S true, A true, B false. All you have to do, just do this. Okay, A true, B false. This is what you have to do. Remember, can you make A true, B false simultaneously? If you can do, then S will be invalid. If you can never do, if it is impossible, then S will be valid. So all you have to do this. Like for example, this question is there. Let's solve this question with the same method. First of all, you take the domain, because this is a first order logic expression, right? This S, did you notice this S? This is a first order logic expression. So because this is a first order logic expression, so there is a domain. So let me take, this is the domain. Okay, I am taking a domain. Now assume that domain is this, like these are the elements in the domain, A, B, C, D and something. I don't care about the remaining. Okay, so there can be some more. So let me assume this is the domain. Now what you have to do? Now remember, this is your A. Understand, this is the A. This is the implication statement. A implies B. So what you will try to do? Can you do this? Can you make A true and B false? This is what we will try to do. Okay, remember, this is what we will try to do. That can you do this? Is it possible or not? This is the simple question. Is it possible? This is the simple question, that is it possible that A is true, B is false? Is it possible? So let's see. Tell me one thing, simple question I am asking. How can you make this true? I want to check, is it possible A true, B false? Is it possible? This is what I want to check. Now you tell me how to make this true. This A, look at, focus on A, forget about B, focus on A. How can I make this A true? To make this true, for every element I have to make P true, right? Okay, for every element I need to make P true. Sorry. So for every element I need to make P true. For every element. I need to make P true, P true, P true, P true. Okay, now you tell me, what about the remaining? Now, okay, so now this is true. This is the only way. Now this we have done true. Now you can see that A we can make true. No problem. This is the only way. Do you agree that this is the only way? Tell me. Do you agree that this is the only way to make A true? Because we want to make A true, B false. This is what we want to do. This A we want to make it true. This B we want to make it false. So to make it true, what we have to do? For every element in the domain, we have to make P true. For every element in the domain, this P must be true. So you can notice for every element in the domain, this P must be true. This is the only way. Okay. Now you tell me, can you make B false? Now can you make B false? Now this B, now can you make it false? Now this cannot be false. Now automatically you can notice that because P is true for at least one element, now this cannot be false. So if you make this, if you make A true, if A true, then B cannot be false. Then B cannot be false, right? So if A is true, then B cannot be false. Or I can say if A true, then B will be true. Okay, so whenever you make A true, then automatically what will happen? This B will be true. So that is the reason this S is a valid. Okay, so is this possible? The answer is no. So that is the reason this S is a valid, because this is not possible. So that is the reason I can say this S is a valid. Okay, so in this situation I will say answer will be valid. This S is valid. Okay, so now I hope this point is clear. Now we will solve these gate questions. All these gate questions, let's try. So this is a gate to 2005 question from the first order logic, and all these statements are implication statement, right? Agree? So look at all the statements one by one, we will solve. So the question is saying that P comma Q are arbitrary predicates, random predicates. P and P comma Q, these are random predicates. Which of the following statement is always true? Means the question is asking for valid. The question is asking valid. Which of the following is valid? This is what the question is asking. Okay, some statements are given to you, and from these statements, which of them is valid? So let's see one by one. Let's see the first statement. The first statement is saying that, what about this statement? Look at first statement. Let me take the example of statement A. Statement A is this, that for all x px or qx implies for all x px or for all x qx. So this is the statement. For all x, the statement is saying that px or qx, this implies, okay, this implies for all x px, for all x px or for all x qx. So first we will see intuitively. What do you think intuitively? Intuitively you tell me, this statement, does it imply this statement? Okay, let's think about intuitive. First, let's see the intuitive proof. Let me assume P means TV. P means TV. Okay, TV, or this Q means, let's assume this Q means, I can say this P. P means TV, and this Q is basically, you can assume something, maybe you can assume car. Okay, so you can assume this car. So I am saying that for everyone, either they have TV or they have car. For everyone, I am saying at least one of them every person has. Okay, like there is a city in which you have A, B, C, D. These are the 4 people, or maybe these are the 3 people. Now what this statement is saying, this is saying that everyone either has TV or car. Like for everyone either has TV or car, either TV or car, either TV or car. Okay, everyone has this. Okay, so you can see that everyone has TV or car. Like this A, either he has car or he has TV or both. So everyone in this city has at least one of them. Does it mean everyone has TV or everyone has car? Tell me. A simple thing. Let me know. Please tell me. So let me know. Intuitively, this is the intuitive proof that everyone in this city has at least one of these. Okay, there are 2 things, or you can say bike or car. Okay, or I can say bike or car. I can say bike. So everyone in this city has bike or car. Like this person A has bike, this person B has car, this person C has both of them. So let's assume this person A has bike, this person B has car, and this person C has bike also and car also. Okay, so everyone has at least one of them. Does it mean that everyone has bike or everyone has car? Tell me. Everyone has bike. Is this true? This is definitely false. Everyone has car. Everyone has car. No, A does not have car. See, A does not have car and B does not have bike. So this is also false. So you can see that this is true. Still, this can be false. So this is not valid, right? Is this intuitive proof clear? This intuitive thinking, is this clear that what I'm saying? Let's call it. Let me assume that this is a something. This is something. Let me assume this is something X, and let me assume this is something Y. Then I am saying that this X true and Y false possible, right? Correct. This is possible. Do you agree that this is possible? This is possible. So definitely, so I can say this statement A is invalid. This expression A, this is invalid. So remember, this expression A is not valid. The intuitive proof, is this clear? This is the intuitive idea. You can intuitively think that this statement is saying that everyone has, look at this statement, a simple thing. Look at this statement. Just forget about this statement and only look at this. What this statement is telling you, for everyone, either they have P or they have Q. Okay, so you can see here I can say everyone has, okay, everyone has at least one of them. Okay, everyone has I can say P or Q. Everyone has P or Q, or okay, at least one of them or both. So I can say everyone has P or Q or both. So very simple. At least one of them everyone has. Now what this statement is saying? This statement is saying that everyone has P or everyone has Q. That is not necessary. That definitely is not necessary. So you can see that it is possible. It is possible that everyone has bike or car. I have bike, you have car. But it is not. It may not be true. It is not necessary that both of us have bike, both of us have car. Okay, so you can notice this also can be false. This also can be false. Okay, so as you can see in this example, this person A has bike, does not have car. B has car, does not have bike. C has bike and car. Now you can easily see that this X will be true because everyone has at least one of them. But you can notice that this will be false because you can see that A does not. This will be false because B does. You can see B does not have bike, and this will be false because A does not have car. So finally, this is false. The same question you can solve if you don't want to solve intuitively. If intuition is not clear, then also you can solve this question. Let me tell you how. Very simple. You take a domain. All you have to do, just take a domain. Okay, just to take a domain, you take. What you do? Just take some domain like A, B, C, something. This domain you take. Okay, now what you do? Now let's call this X. Let's call this Y. So is it possible that X is true, Y is false? Is this possible? Just tell me, simple question. Is this possible? I am asking, is this possible? Can you make it possible? So let's see how can we make it possible. I want to make X true, Y false. Okay, so you tell me what I have to do to make Y false. Just tell me. Simple question I am asking. What I have to do to make Y false? What I have to do? I want to make Y false. What I have to do? I have to, remember, I have to make this false and I have to make this false. Correct? So these two things I have to do. I need to make this false. I need to make this false. Okay, so now you tell me what I have to make this false. This for all x px. Only focus on this. Forget about remaining. For all x px, I want to make it false. Then for some element p must be false. Correct? So for some element, I can take this element and I can make p false. Okay, now focus on this. Remember, this x has nothing to do with this x. Remember, these two, these are completely independent. These are completely independent. So remember, this x has nothing to do with this x. They are completely in the different scope. This is the scope of this universal quantifier. This is the scope of this universal quantifier. So remember, these are completely independent. Now you tell me. So I can make it false. All I have to do, for some element, I can make p false. So for this element b, I can make p false. Now for to make it false, what I need to do? To make it false, only focus on this. Only focus on this. What I need to do to make it false? I need to make q false for some element. Q false for some element. Remember, that element may or may not be b. I need to make q false for some element. That element may or may not be b because This x has nothing to do with this x. They are completely independent. This is the scope of universal quantifier, this universal quantifier, and this is the scope of this universal quantifier. So what I can do, for this C I can make P false. Now can I make X true? You tell me now. So now you can see that Y is false. So this Y is false. Now you tell me, can I make X true? Yes, obviously I can make X true. For every element I can make one of them true. For every element, at least one of them I can make true. What I can do? For this element A, I can make P true, Q true. For this element I can make Q true. For this element I can make P true. For the remaining elements I can make P true, P true, P true. Okay, for the remaining elements, for all the remaining elements I can make P true, P true, and so on. Okay, so now you can see that X is true, simultaneously Y is false. So yes, this is possible. So that is the reason I can say, because this is possible, so this A is invalid. Did you understand? Please tell me. Both the proof we have seen, intuitive proof and also this intuitive proof also we have seen, and the other proof also we have seen. So this is definitely invalid. Let me give you just one more proof. Let me give you one last proof so that you will get a lot of confidence by this proof. Now consider this scenario. Okay, let's consider this X. Let's consider this let's consider this something like Y, or I can say I can consider this M, and let me consider this N. Okay, so you can see. Now you tell me, I am asking, let's assume the domain is this. I am giving you this domain. Domain is set of natural number, and let me assume Px is X is odd, and Qx is X is even. Okay, Px is X is odd, Qx is X is even. Now you tell me, in this situation you tell me what is this X in this situation, or I can say maybe I can say let's call it I, whatever, like M and okay, let's call it S. So you tell me what is S in this situation. In this situation, your domain is set of natural number, P is X is odd and Q is X is even. In this situation, what is S? What is this S? This S is saying that for everyone, either P is true or Q is true. For everyone, at least one of them is true. For everyone. For everyone, can I say at least one of them is true? Yes, of course. So this S will be true. What is the truth value of M? What is the truth value of M? Can I say for everyone? For everyone, can I say everyone is odd? Can I say for everyone in the domain everyone is odd? Can I say? No, definitely. So this is false. What about N? Can I say everyone is even? In the domain for everyone, can I say everyone is even? Can I say? That is also false. So you can see that M or N is also false. M or N, that is also false. So now you can easily see S is true. So okay, S implies M or N. This is definitely what? This is definitely invalid. Is this clear? So this is definitely invalid because S is true and M or N is false. So this is another proof. So 3 proof we have seen. Why I am telling you all these 3 proof? Because it will give you more understanding about these questions. All these questions you can solve intuitively. Okay, every question, each of these questions you can solve intuitively. If you solve intuitively, it will take less time. You can solve the question very quickly. Okay, so like this you can do. So very simple question. Now anyway, this A is invalid. What about B? B is saying that for everyone Px implies Qx implies for everyone Px implies so let's see this option B. What this option B is saying? Option B is saying that for everyone Px implies Qx implies for everyone Px implies for everyone Qx. Okay, so this is the statement. Look at this statement and now let's solve it. What this statement is telling you. Now let's solve this question. For everyone, Px implies Qx. Now what I do? In this question, first of all, let's solve this question with our method. With our method, let's solve. What is our method? Our method is what you do. You let's assume that this is A. and let me assume this is your this is B, or I can assume, you can assume like this. This is M, this is N. Okay, so finally I can say this M implies N. Okay, this M implies N. This is what you have. This M implies N. Let me call it B. Let me call it B. Now, what you do? Now you take a domain. Again, very simple method. All you have to do, just take a domain. The domain you can take, let's, for example, A, B, C, and so on. So this domain you can take. Now what you do? Now what you have to do? Tell me. In this situation, can you make this? Is it possible that A is true, B is false? A is true and B is false. Is it possible? A simple question I am asking. Is it possible that A is true, B is false? So you tell me, very simple question. To make, so what I want to do? To make B false, what I need to do? You tell me, simple question. To make this, what I need to do? If I want to make this B false, this B I want to make false, what I need to do? B is this. M implies N. I want to make it false. What I have to do? So I need to make M true, N false. Okay. I need to make this. What I need to do? I need to make M true, N false. Now you tell me, if I make M true, then what will happen? This is M. This is M. Look at M. I want to make M true. So what I need to do? For every element in the domain, P must be true. Okay, for every element, what should happen? This P must be true, this P must be true. For every element, this P must be true. For every element. Okay, now let's see. I want to make this N false. This is N. Look at this. This is N. I want to make it false. So what I need to do? For some element, I need to make Q false. For some element. So what I can do? For this element, I can make Q false. Now you can notice this is done. Now what we have done? B is false. Okay, because for some element I need to make Q false. For this element B, I can make this Q false. Very simple. So now you can see that M is true, N is false. So M implies N, that is false. So this B is false. Now can I make A true? Simple question. Can I make A true? Sumant, Ratul, tell me. Can I make A true? This A, look at this A. Can I make it true? What I need to do? For every element, either P must be false or Q must be true. Yes or no? What this A is saying? This A is saying that, look at this A. This A is saying that for every element, either P must be false or Q must be true. Okay, for every element, either P must be false or Q must be true for every element. But this is not possible, right? Because of B. Because of B, this is not possible, correct? For B, for this element B, you can see that this will be false for B. Look at this. The internal. This will be false for B. So automatically this A will be false. Correct? Is this clear? So you can see this is actually false. And who is the counterexample? This is actually false. And who is the counterexample? The counterexample is because of B. Because of this will be false. So you can see that this is possible. The answer is no. This is not possible. Because this is not possible, so this B is valid. So this B is valid because this is not possible. Is this clear? So remember this statement number 2, this is valid. Because it is not possible. This is the method. Did you understand? Please take your copy pen. If you want to solve it, very quickly if you want to solve it, please take your copy pen. Okay. Now let's see. Let's see another question. The next option C. Look at option C. Option C is saying that the reverse direction. Option C is the another direction. This direction. Okay. In the option C, you have this direction. In the option C. So in the option C, what you have? This is your, I can say this is your B, and you can see this is your A. Okay. You can see this is your A. So in the option B, you have in the option C. Again, the same question I am asking. Can you make A true and B false? Can you make A true, B false? Can you do that? Can you do that? A true, B false. Can you do that? Is it possible? Do your best. Okay, try your best. Can you make it possible? Again, you can, what you can do, you can take a domain. The domain you can take is like A, B, C and so on. This domain you can take. Now, what I need to do if I want to make A true or and B false? Remember, this is B, this I want to make false, and this is A, this I want to make true. Can I do that? First of all, to make B false, what I need to do? Sumant, Ratul, tell me. I want to make B false. What I need to do? This B. Look at this B. Only focus on this B. This B I want to make false. This I want to make false. What I need to do? For some element, this must be false. For some element, this internal thing must be false. For some element. Okay, for some element. For this element, this internal thing must be false. This internal thing will be false. It means for some element means this element B. For this element, P must be true, Q must be false. So for this element, P must be true, Q must be false. Okay. Now you can see this B is false. This is done. B is false. This is done because for some element, if I want to make this B false, this B I can make easily false. If for some element this internal thing must be false, let's assume that element is B. For B, this internal thing must be false. So for B, this P must be true, Q must be false. Okay. Very good. So this we have done. Now you tell me a simple thing I am asking, that can you make A true now? Now can you make A true? Remember, automatically, can you make A true? Let's try to make A true. You can easily see this will be what? You can easily see what is this? Because for some element Q is false, so definitely this is false, right? Correct? This is definitely false. Okay, because for element B, Q is false. Correct? You can see for this element B, look at this element B. For this element B, Q is false, so definitely this will be false. What about this? Can I make it false? Because remember, I want to make A true. My target is to make A true. This is my target. This is my aim. This is my purpose, to make A true. But we already know that this is false because for B element Q is false. So automatically this is false. Now what I have to do to make A true? If I want to make A true, then I need to make it false. Can I make it false? Can I make it false? This, can I make it false? Of course I can make it false. All I have to do, just for this element I can make P false. So yes, this false is also possible. And false implies false. So you can see this A is true. So is this possible? The answer is yes, this is possible. Because this is possible, so I can say this option C invalid. This option C is invalid. So you can easily see that answer will be option C. So this option C is invalid. So you can just cross it. Okay. Did you understand? Please tell me. See, very simple question. For every option, I am giving you the analysis. Now the option is this. Now the option is this, that for all x, px, this implies this one. Okay. So let's see option D now. Focus on option D. What option D is saying? Look at option D. So this implies this one. Now let's check. So I'm giving you option D, that is for all x px, double implication for all x qx. Okay. For all x px, this implies. Okay. This implies. So you can see that this implies for all x px double implication qx. For all x px double implication qx. Okay, let's see, is this valid or not? Again the same method, nothing changed. Same method. What you do? Again you take a domain. The domain is A, B, C something. This is your domain. You take a domain. Now what you do? Now remember, this is your, I can say this is your B and this is your A. This is the A. Okay, so is it possible that A is true, B is false? Is it possible A is true and B is false? Is this possible? Simple question. Is this possible? Is this possible that A is true? Now you tell me. Now you tell me this one. Is this possible that A is true, B is false? Let's check. So you can see that. Tell me, how can I make, I want to make A true, B false. This is what I want to do. Okay, is this possible? Let me check. If I want to make A true, then what I have to do? You just tell me simple question I'm asking. If I want to make this A true, B false, this is what I want to do. First of all, you tell me about this B. What I can do? I want to make B false. For this, what I can do? B false. To make B false, Ratul, what I can do to make B false? This is the B. Look at this B. To make this B false, what I can do? So if you want to make it false, then for some element, this thing must be false. For some element, this thing must be false. Let's assume that element is C. For this element C, this thing must be false. It means for C, this P comma Q must be different. For this C, P comma Q must be different, remember, right? Yes or no? This P comma Q must be different. Okay. Now you tell me. Now you can easily see that B is false. This B we have created false. Now you can easily see this, or this is also false. Now this is also false because for some element this Q is false. So you can easily see that this also will be false. For all x qx, this will be false. Easily you can see, because for element C, Q is false. So definitely this, for all x qx, this also will be false. Now, can you make A true? If you want to make A true, you need to make this also false. Can you make this false? Is it possible? You can make it false. Of course I can make it false. For this element A, I can make P false. So of course this is also false. So you can notice false, double implication false, false, double implication false. That is your A. That is your A, which is a true. So yes, this is possible. The answer, yes, this is possible. And if this is possible, then it simply means that because of this yes, you can say this D is invalid. This D will be invalid because of this yes. So I can say this D, this is invalid. So this is your answer for this question. Answer is option B. Okay, understood? Let me know. So like this you can solve. So see, 4 questions I have done. I hope that you can do the remaining questions. And if you do more, if you want more questions, more analysis, then you can refer to the Go Classes Discrete Mathematics course. I hope this question is clear. Please tell me, Ratul, Sumant, Sukesh, okay, Lokeswar, please tell me. Everyone, please let me know. So did you understand the analysis of all the 4 options? Each of the 4 options we have seen, did you understand the analysis? Are you confident that you can solve all the questions? Whatever questions will come, whatever operator they give you here, like here you have or, here implication, here double implication. So whatever operator they give you, can you handle it? Tell me, are you confident that you can handle it? Okay, very good. Now let me give you, see, if you solve like this, the proof idea we have seen. Okay, if you do like this, then you can create a table. Let me tell you. Okay, what I'm telling you, this proof, understanding proof is very important. Okay, so for the last 4 questions, I have given you the proof, the formal proof, very easy proof I have given you. Understanding the proof is very important. Okay, is very important. That is very important. Did you understand this proof was so simple? Yes or no, Ratul? Correct? Sumant, this proof was so simple. Yes or no? Because all you have to do is simple calculation. Simple concept you have to apply. Every concept, like how can I make it false, make it true, make it false, make it true. So all you have to do, just apply the concepts of universal quantifier, apply the concepts of these operators. So very simple. So remember, understanding the proof is very important. This is extremely important. So, but you can create a table now. If you understood the proof, now after understanding the proof, you can remember these things also. Okay, remember this point. After understanding proof, after understanding proofs, you can remember these also. Okay, these standard things you can remember also. These standard, I can say these standard these standard things must be remembered also. Okay, because in the GATE exam, if you try to prove all of them, it will take a lot of time, right? Yes or no? In the GATE exam, if you try to prove all of them, so if these standard things are coming in the GATE exam, then you can remember these also. After understanding the proof, this is very important. Because see, some students, they don't want to understand the proof, they directly want to buy heart. I am telling you, they directly want to remember. I am telling you, after understanding the proof, you can remember. First, you understand the proof. Now, let me tell you, you can create a table now. Okay. So, a simple, now I am giving you a table. This table actually, you will not find anywhere. This table, you will not find anywhere. And if you find this table anywhere, then it simply means they have taken from Go classes, because this table I have created. Okay. I solved all the 48 questions. Let me tell you, 48 questions I solved. Okay, after solving 48 questions, this table I have created. After proving 48 questions, I have created this table. So if you find this table anywhere, then definitely it is taken from Go classes. Okay, so let me tell you this table. Again I am telling you, note that proof is important. Okay, note that. Okay, understanding proof is important. Proof is important. So, of course, you should understand the proof. After that, you can remember this table. Okay, first you understand the proof. In this table, there are, let me tell you, in this table, there are 48 questions. In this table, 48 questions are answered in this table. Now, let me give you this table. Let me quickly give you this table. So, now consider this type of situation. Let's assume this is a quantifier. Okay, I can say this psi is a quantifier. I have this type of statement, psi x, px, this some operator, qx. Okay, and and what I'm saying, so this is your, tell me which of them is expanded and which of them is and you have psi x, px, hashtag psi x, qx. Tell me which of them, look at these two and tell me which of them is expanded and which of them is compact. Which of them is expanded and which of them is compact? Tell me. Let me know. So you can clearly see, let's call it expanded. Sorry, let's call it compact, because this is compact, right? Okay, let's call it compact. You can easily see that for all x, this is a compact and this is a expanded. Okay, so let me call it compact. Let me call it compact and let me call it expanded. Okay, so I am calling it compact and I am calling it expanded. Now what I am saying, that just assume that compact is on the LHS. Assume that compact is on the LHS. Assume that this expanded on the RHS. This assumption you make. Now here what I am saying, this is a quantifier. This is a quantifier. Either this can be for all quantifier or this can be existential quantifier. And remember, this is a logical operator. This is a logical operator. This can be and, this can be or, this can be implication, this can be by implication, exclusive or, this can be NAND, this can be NOR. Okay, so these are the logical operators. Now, this table I am giving you, very simple table, and this table is like this. What you can do? So on this side, I am writing the, on this side, I am writing the, what I am writing is quantifier. So universal quantifier, existential quantifier. Okay, like this I am writing. This is universal, this is existential. And on this side I am writing the operators. Operators I am writing like this, in the order of precedence. In the order of precedence, like and, then or, then implication. Now you can automatically notice that with implication, who is similar to implication? Who is similar to implication? That is by implication. Okay, who is similar to by implication? By implication means exclusive NOR. So who is similar to exclusive NOR? Who is similar to exclusive NOR? That is exclusive OR. Then you have NAND, then you have NOR. Okay, so very simple. So this is how you can create this table. You have NAND, this is NOR. Okay, now let's see. Now you can easily see, very simple. I am telling you that for arrow type operators, which of them are arrow type operator? Tell me. Which of them are arrow type operator? Like this is arrow type operator. These are the arrow type operator. For the arrow type operator, this universal quantifier will only go from compact to expanded. It will only go from compact to expanded. Okay, it will only go from compact to expanded. Now let me tell you that here it will go in both the direction. Here it will go in both the direction. Here it will go in this direction. It will go in this direction. Okay, so like this you can remember. If you want to remember, you can remember like this. And so you can okay, so like this. Now the remaining table, you can fill this remaining table easily, you can fill this. So this is your table. I hope this table is clear. Okay, because see, let me tell you, this table has been proven. I have proved it. Many of the Go classes students have proved it. So this table is proven. Okay, this is proven by me and many Go classes students. This is proven, and there is some kind of symmetry. So this table will help you a lot. Okay, this is definitely going to help you a lot for many questions. Let me tell you, in this table there are total 48 questions, right? Yes or no? How many questions are there in this table? In this table there are, you can see, there are 7 operators, 2 quantifiers, and both the directions. Okay, 7 operator, 2 quantifiers. So you can notice 7 operators, 2 quantifier, and 2 directions. So how many questions? Okay, 28. Okay, sorry, 28 questions are there. In this table, there are 28 questions in this table. So in this table, there are 28 questions. But I am not telling you to buy hard. Please, please, please don't buy hard this table. You have to understand the proof. This table has been proven by me and many Go classes students. They have proven it. Okay, but if you want to remember, you can remember like this. So I hope this point is clear. Whatever you do, this table will definitely help you in a lot of questions. Okay, like for example, let me ask you some questions. Please take down this table. Write down this table in your notebook. Then I will ask you a lot of questions. Remember, in this table, my assumption is, what is my assumption in this table? I am assuming what I am assuming. In this table, what I am assuming? In this table, I am assuming that LHS has compact. LHS is compact side, and I am assuming RHS is expanded side. This is my assumption in this table. In this table, I am assuming that compact side and expanded side. So this means that compact to expanded. This means expanded to compact. This means compact to expanded. This means expanded to compact. This means both the directions. Compact to expanded, expanded to compact. This means none of the directions. Neither from compact to expanded nor from expanded to compact. This means no direction. This means from compact to expanded. Okay, so this is my assumption that LHS is compact expression, LHS is compact expression, and RHS is a expanded operation. Let me ask you this question. For all quantifier Px, NAND, Qx, okay, is this true or false? For all x Px, NAND, for all x Qx. Is this true or false? Tell me. Look at this and tell me, is this true or false? So you can check it out in the NAND. This is a NAND operator. So you can see this is a NAND operator. And you can see this is your universal quantifier. So psi is equal to universal quantifier. You can easily see this is a compact side. On the LHS you have compact side. You can see that on the here you have expanded side. But remember, I am asking that, is this implication true? Is this implication true? So you can see that universal quantifier, NAND operator, it should go from where to where? Tell me. It should go from where to where? It should go from compact to expanded. Universal quantifier, NAND operation, it should go from compact to expanded. Compact to expanded you should go. You cannot go from expanded to compact. So this is definitely invalid. This is definitely invalid. But if I do this, this will be valid. If I do this, this will be valid. And if I do this, this will be invalid. If I do this, this will be invalid. So like this you can do. I hope this point is clear. Like, let me ask you one more question. Let's see this. There exists x Px. There exists x Qx. Okay, this side there exists x Px exclusive or Qx. Now you tell me, what about this? Is this true or false? Is this valid or invalid? Look at this and tell me. Now again you can notice this is expanded. This is expanded. you can see this is compact, this is compact, this is expanded. Okay, and you can see operator is what? Operator is this is the operator. Operator is this exclusive OR, and this is existential quantifier. Psi is equal to existential quantifier. Now you tell me, is this valid or not? So you can notice in the existential quantifier, this is existential quantifier, this is a exclusive OR. So we should go from expanded to compact, right? Correct, Ratul, Sumant? Correct? Yes or no, Sukesh? So we should go from expanded to compact. This is what we should do. From expanded, we should go to compact. Yes, we are going from expanded to compact. So this is actually valid. This is valid. In the same question, if I do this, this will be invalid. In the same question, if I do this, this will be valid. This also will be invalid. Okay, so like this, you can use this table. Now let's solve this question. What is the answer for this question? But remember, proof is very important. Okay, so this point you have to remember. Let's see this GATE 2016 question. You don't have to remember the table. There is no need to remember the table. You should understand the proof so that any question comes in the GATE exam, you can handle it. Okay, now let's see. So this is a GATE 2016 question. Let's check it out. Which of the following well-formed formula is not valid in the predicate calculus? Which of them is not valid? Let's check it out. So first, let's see the option A. What the option A is saying. Option A is actually very simple. For all x, px implies for all x, qx. So this is given that for all x, px implies for all x, qx. This side is given to you. This implies there exists x negation px or for all x, qx. There exists x negation px or for all x, qx. Okay, this is the statement that is given to you. Now very, very simple. Now you can see, please tell me one thing. This table will not help you if in many questions, correct or not? So that is the reason you should not by heart this table. Do you agree? This table will not help you in many questions. For example, if I mix the operators, it will not help you. Right? Yes or no? On the compact side, I give you this operator. On the expanded side, I give you this operator. Then this table will not help you. Okay. So this table is not going to help you if they create some variation. If they mix the operators, they mix the quantifier. Like if they mix the quantifier for all and there exist, these quantifiers they mix. These operators they mix. If they do this type of mixing, then definitely this table is not going to help you. So that is the reason I am telling you again and again that understanding proof is very important. This table will help you in some situations. It will save you time. But remember, this proof, if you understand, then it will be helpful in all the situations. In every situation, you will be able to solve the question. Okay. In every situation, whatever variation they ask you, whatever question they ask you, you can solve it. So this table is not for by hearting. If you are by hearting this table, it will not help you. But if you are understanding this table, if you are understanding the proof, then it will help you. Now let's see this question. You can see they are mixing, right? Universal quantifier, existential quantifier are mixing. You can notice implication and disjunction. So they are mixing. In this question, they are mixing. Okay, now let's solve this question. So first of all, what you can do, what this question is asking, let's check it out. So first, actually, you can do the you can simplify this. Okay, we already know this statement. We already know that alpha implies beta. That is same as alpha dash or beta. Correct. So this thing you can apply and you can solve it. So this will become what? This LHS. Okay, let's call it LHS. This is LHS of implication. This is RHS of implication. So first you simplify this LHS. What the simplification will be? Negation of this or this. So it will be negation of universal quantifier this or for all quantifier QX. Correct? Now what is this? We already know that universal quantifier negation, if I do, that will be same as existential quantifier negation PX. Okay, so that also we know. So what you can do? Here you can apply this. So here you can apply this. So it will be, in this you can apply. So it will be there exist x negation px or for all x qx. This is same as rx. This is same as RHS, right? If you notice, this is LHS. this LHS is same as RHS, this is same as RHS, so this is actually valid. Okay, so this implication is also valid. Remember, this implication is also valid. I am telling you, this implication is also valid. This by implication is also valid. This implication is also valid, and the by implication is also valid. So all these are valid. So if the question is asking for by implication, that is also valid. This is also valid. So for this question, you can easily see that this is definitely valid. Now let's see what is the next point. What is the next question? Here you can apply the table. In this question, the table will help you, right? Okay. So can you prove it? See, using the table, you can see that this will be what? This existential quantifier in the case of or. So this, if you remember, the table we have already seen. If you remember this table, for all, existential quantifier, and or, then this table we have already seen that this is by implication, this is a backward implication, this is by implication, and this is a forward implication. So this table we already know. So you can see that in the case of or, okay, so it will be by implication. So you can see this is valid. From the table you can easily see this is valid. Okay, actually this by implication is also valid. You notice one thing, that if this is valid, you can notice that what this P, or I can say what this A double implies B means. This A double implies B, this is true, or I can say this is valid if and only if both are valid. A implies B, this is valid. B implies A, this is valid. If both are true, both must be true. Okay, so this will be valid if and only if both are valid. I can say this thing is valid. This thing is valid if and only if both the things are valid. Okay, so very simple. Now let's solve this. So you can see this will be valid, but let's prove it. The question number B, don't by heart, let's prove it. So the question number B is like this: existential quantifier. In the B, he is saying that expanded implies compact. Expanded to compact. Let's see this. So the question is saying that for some person Px, intuitively can you prove it? Can we prove it intuitively, like without the formal proof? Can we prove it intuitively? So let's see the intuitive proof first. The intuitive proof is very simple. What this is saying? This is saying that for someone P is true or for someone Q is true. Okay. So for example, this is saying that either someone has maybe I can say either someone has bike or someone has car. Okay, either someone has bike or someone has car. Very simple. So what this is saying, there are three people in this society. There are three people, let's assume, in this city. Now we are saying that someone has bike or someone has car. Okay, someone has bike or someone has car. Now you tell me, can I say someone has bike or car? Let me know. If someone has bike or someone has car, this information we know that these people, someone has bike or someone has car. Okay, either someone has bike or someone has car. Then can I say that someone has bike or car? Yes, definitely. For example, let me assume that this person has bike. If this person has bike, then automatically what will happen? This will be true. Okay, let's call it X and let's call it Y. So you can easily see that this X will be true. If you have if someone has bike, automatically Y also will be true. So if X is true, then automatically Y will be true. Correct? Yes or no? So this is the intuitive proof that this B is valid, because if someone has bike or someone has car in this city, okay, there is at least one person who has bike or there is at least one person who has car, then definitely there is at least one person who has bike or car. This is the intuitive proof that this B is valid. So whatever you do, this B will be valid. Now, the same thing we can prove using our method. If you don't want to prove like this, you can prove using our method. Let's take a domain. The domain you can take as A, B, C, something like this. This is the domain you can take. Now what you can do, all you have to do, look at this. Let's call it A and let's call it B. Can you do this, that A true, B false? Can you do? Can you make A true, B false? Is this possible? Just ask yourself, is this possible? Is this possible? So let me check. First of all, you tell me how to make B false. This B, this is the B. Look at B. Only look at B. How to make it false? To make it false, what you will have to do, look at this and tell me. Look at this and tell me. To make it false, what you have to do? This is existential quantifier. If you want to make it false, then for everyone this must be false. For everyone P or Q must be false. For everyone. For this, for this, for this, for this, for everyone P or Q must be false. P or Q is false, it means P is false and Q is false. So for everyone, if you want to make this, if you want to make B false, then for everyone P must be false, Q must be false. For everyone P must be false, Q must be false. Remember? For everyone P must be false, Q must be false, and so on. For everyone this would happen. Now can you make A true? Now can we make A true? Now you can notice easily that now this will be false because for everyone Q is false. Okay, for everyone you can notice Q is false. Also for everyone P is false. For everyone P is false. So you can see that this is also false. So false or false, that is false. So is this possible? The answer is no. Okay, is this possible? The answer is no. So you can see this option B is valid. So this is how you can prove. Okay, very easy to prove. I hope this point is clear. Can you intuitively prove it? What about the other side? What about this side? Can you intuitively prove it? The intuitive proof, can you give me? Yes, of course you can intuitively prove, because for someone I am saying that either for someone has bike or car. Let's assume this is bike and this is car. I am saying that someone has bike or car. There are some people, like I am saying that there are some people A, B, C. There is someone, let me assume this person. There is someone who has bike or car. So let's assume this person has car. Okay, because this statement, look at this statement. This is saying that someone has bike or car. Okay, so let's assume that someone is B. So this B has bike or car. So let me assume this B has car. Then automatically what will happen? Because this B has car, so automatically this will be true. So automatically, because there is a or here, so this whole thing will be true. Okay, so you can see that if this is true, then definitely, if this is true, if you make it true, then automatically this will be true. So in this situation, I can say this is also valid. Okay, so this direction is also valid. This is the intuitive proof. You can easily see that this direction will be valid. The formal proof, can I give you as a homework? The other proof, the formal proof, like the intuitive proof we have seen, the formal proof, can I give you as a homework? If you have any doubt, you can ask in the comment. Any doubt you can ask in comments. If you have any doubt, then you can ask in the comments. Okay, so now let's see. So this I can give you as a homework. I know that you can do it because a lot of questions we have done. Now let's see this. So this is definitely valid, and remember the other side is also valid. So let me tell you that this side is also valid, this side is also valid, both are valid. Okay, what about the next question? In the next question, you can apply the table. The table, what the table is telling you? The table is telling you that this existential quantifier, in the case of AND, it will go from compact to expanded. We will go from compact to expanded. Or from compact to expanded. So this is valid. This is valid. Okay, what about this one? In the case of universal quantifier, in the case of OR, it will go from expanded to compact. Okay, in this case, you can notice universal quantifier, in the case of OR operation, it will go from expanded to compact. Okay, expanded to compact. So definitely this is invalid. Okay, this statement is invalid, so the answer will be option D. This D is invalid. But let me prove option D. So let me do this. First of all, this valid, I can give you this as a homework. Okay, take this as a homework. But this option D I can take. Let's see this. So from compact to expanded, this side is given to you. Let's see this option D. Option D is saying that for all x, px or qx. For all x, px or qx. Does it mean for all x, px or for all x, qx? Oh, sorry. This actually we have already done. This actually we have already done, because you can see that here I am saying that there are some people, let's assume ABC, and this means bike. Let me assume this means bike and this Q means car. Now what I'm saying that everyone has bike or car. Everyone. Like let's assume this has bike, let's assume this has car, and let's assume this has bike and car. So everyone has bike or car. This statement is saying like this. Remember, for everyone, they either have bike or they have car. At least one of them, everyone has some traveling, some vehicle they have. Everyone. Okay, everyone has at least one vehicle, either bike or car. Does it mean that everyone has bike? Does it mean everyone has bike? No. So this is false because you can see that B does not have bike. And you can notice this is also false because does it mean everyone has car? A does not have car. So you can easily see that this option D is invalid. Okay, so like this, you can solve the question very easily. And for this question, the answer will be option D. The question is asking for invalid. That will be option D. So like this, you can solve a lot of, okay, I hope that you understood all these things. Now let's see this question. Quickly tell me, from the table you can solve it. What about the first one? Px implies Qx implies. So yes, this is valid. From the table you can check this will be valid. Okay, you can check it in the table or you can prove it. You can try to prove it. I give you as a homework. You can try to prove it. The second thing, in the second, can the table help you? Tell me. In this option B, can the table help you? No, the table cannot help you because operators are mixed. You can notice that here you are taking, here you have or operator, here you have implication. So operators are mixed, so table cannot help you. So let's take this option B. Let me take this one, option B. Option B is saying that there exists some for which Px or Qx is true. Does it imply that there is some Px implies there exists some Qx? Okay, let's see this one. Let me check this one. So again, here you can apply the method. All you have to do, just apply the method. Method will always help you. What you do, you take a domain. You can take this as some m, and you can take this as some n. So can you do this? Can you make this that m is true and n is false? Can you do this? M true, n false. Can you do this? Tell me. Is this possible? Is this possible? Is this possible? Let's check. So again, you take the domain like A, B, C and something, some domain you take. Okay. Now you can notice that. Tell me how to make this n false. I want to make n false. This n, I want to make it false. So how to make this n false? If I want to make this false, then I need to make it true, right? I need to make it true. So for some person P must be true. For someone, okay, remember, for someone P must be true. I need to make this false. So for everyone Q will be false. For everyone, remember, for everyone Q will be false because I want to make it false. So for everyone Q will be false. Okay, because you want to make it false. So existential quantifier, you want to make it false. So for everyone Q must be false. Now you can notice this. This is done. Okay, this activity is done. Now you tell me, can you make M true? This M, can you make true? Existential quantifier, for some student, can I say, for some element in the domain, can I say this is true? Yes, of course. Yes, of course. You can see, yes, of course. So you can easily see that now this is true. So yes, this is this possible? The answer is yes. Is this possible? The answer is yes. So I can say this option B is invalid. Very simple. Okay, is this clear to everyone? So this option B, this is invalid. Okay, the question is asking for valid, so definitely answer will be option A. This is a GATE 2007 question. Okay, now let's see the next. In the next question, you can apply the table. Using the table, you can do that this will be invalid. From the table, you can check it or you can prove it. There is no problem. You can prove also. And from the table, you can check that this will be invalid. Tell me, in this option C, which direction will be valid? The forward direction or backward direction? Which direction will be valid in this option? Option C. which direction is going to be valid. So existential quantifier, this is the table if you remember. Okay, there is a universal quantifier, there is existential quantifier. This was the table, and or implication, this type of table was there. So you can notice there was by implication here, there was by implication here, there was forward implication, backward implication, this. So this type of table you had. So now you can easily see that in the case of existential quantifier, and you are going from compact to expanded. You are going from compact to expanded. So the forward implication will be correct. Okay. In this option C, the forward implication is valid. Remember this point, I can say that forward implication valid. Forward implication is valid. Okay. The backward implication is not valid. So this double implication is invalid. Okay. Let's see the option number D. This is interesting. This is a this option number D. This is basically a nested quantifier question. For all x there exists y. For all x there exists y implies there exists y for all x. Okay. So this is the statement. Let's see option number D. What this option D is saying? This is saying that for all x there exists y pxy. This implies there exists y for all x pxy. Okay, let's check. Is this valid or not? What do you think? Is this valid? See, very easily, can you make it true? Still can you make it false? Like here we are saying that for remember, you have to take the same domain. Please understand, you have to take the same domain. Is this possible? Can you make it like, let me call it A, let me call it B. Is it possible that A is true, B is false? Can you make it possible? Can you make it possible? Is this possible? A true, B false. Is it possible? Remember, for X you have to take the same domain as okay, so for this. So let me assume like ABC, ABC, something like this. And you can notice that, can I make this A true? If I want to make A true, then for everyone there must be someone. For everyone there must be someone such that for everyone there must be someone. Remember, for everyone there must be someone such that this PXY is true. So you can notice that PAA true. You can notice PAA true, PBC true, and let's assume PBC true and PCB true. Okay. So this is the, now is it possible? What about B? In this situation, what about B? Let's assume for A you have A. So this is the thing, that for everyone someone is true. For everyone there is someone. For everyone there is someone means for A there is A, for B there is C, for C there is B. So you can notice PA true, PBC true, PCB true. Now is it possible that this can be false? Is it possible? What this is saying? This is saying that there is someone. What this is saying? This is saying that there is someone. Okay. For everyone there is someone. There is some fixed y. Okay. Remember this. What this is saying? There is some fixed y. There is some fixed y. Okay. This is what this is saying. So there is some fixed y. Fixed y such that, this is important, some fixed y is there such that what is happening? For everyone this PAY is true. This also must be true. PBY must be true. And PCY must be true. This is not mandatory, right? So this is possible, that this is possible. Yes. Correct. This is definitely possible, because you can make it false. It is possible you can make it false. Are you getting my point? What I am saying? Very simple. If you are not understanding, let me take a concrete example. Consider that this domain is set of natural number. For a moment, let's consider domain is set of natural number, and let me assume that PXY. What is this PXY? So this PXY is, let's assume X is less than Y. Okay. This X is less than Y. Now, in this situation, what will happen? This will be true, correct? Look at this. In this situation, if my domain is, forget about this. Oh, okay, forget about this. Only look at this. Okay, domain is set of natural number, and PXY is X is less than Y. Can I say for every natural number, for everyone there is someone? Can I say? Can I say for every natural number there is someone such that x is less than y? Can I say this? For every natural number 1 2 3 4, for every natural number, can I say there is someone x y? Can I say there is someone such that x is less than y? Can I say for everyone? Can I say there is someone? Yes, yes, for everyone there is someone such that x is less than y. So this is definitely true, correct? Yes or no? Agree? Do you agree that this is definitely true? This is definitely true. Okay, this is definitely true. Forget about this one, forget about this RHS, forget about it. Now let's talk about this, only RHS. Let's talk about this. Can I say there is some natural number? Okay, remember, can I say 1 2 3 and so on? Can I say there is some natural number? For every natural number, whatever natural number you take, such that pxy means x is less than y, is there any natural number? There is some natural number such that every natural number is less than this. Tell me, is this true? Is there some natural number, is there some y such that for every x is less than y? Means some natural number which is greater than every natural number. Tell me, is there some natural number which is greater than every natural number? You tell me this simple point. Okay, what this means? This means that some natural number is greater than every natural number. Tell me, some natural number is greater than every natural number. So definitely this thing, look at this thing. This is definitely, I can say, false. Okay, some natural number is greater than every natural number. This is definitely false. Can I say infinity is greater than every natural number? Can I say, can I take y equal to infinity? Can I do this? Can I do this? Y equal to infinity, can I do? Can I do this? Please tell me. Can I take y equal to infinity? And can I say that, yeah, okay, yes, yes. So infinity is greater than every natural number. Can I say this? Can I do this? Can I take infinity and can I say infinity is greater than every natural number? No, because infinity is not a natural number, remember. Okay, many times I have told you this, but remember this point. Always you understand that this infinity does not belong to natural number. This infinity is not a real number. This infinity does not belong to set of real number. This infinity is not a natural number. This infinity is not an integer. You cannot take infinity. Remember, infinity does not belong to the domain. Your domain is set of natural number. And please understand, infinity does not belong to the domain. Infinity is not a real number. Infinity does not belong to natural number. So infinity is not a number. So remember, you cannot take infinity. So you can easily see that, can I say there is some natural number which is greater than every natural number? The answer is false. So what you found that in this situation this is true, in this situation this is false. So finally this true implies false. Okay, in this situation I can say that this is a false. So this option D is invalid. Okay, is this clear? So this option D, this will be invalid. So this is your answer, that this option D, this is also invalid. The question is asking for valid and the only valid statement is option A. So option A will be the answer. So this is a beautiful question. You can solve it very easily. Okay, let's move on. Let's see this one. Tell me the answer for this question. Consider the following first order logic formula. A formula is given to you whereby R is a binary relation. This is a binary relation, you can notice. And the question is asking, is this valid or satisfiable? So this R is some relation. This R is some relation, remember. This R is some binary relation. Or I can say R is basically some relation. R is a relation. Now, what is this definition of? Do you remember what is the definition of? That for every x, for every y, if x is related to y, then y is related to x. If x is related to y, then y is related to x. What is the definition of? This is the definition of symmetric relation, right? Yes or no? This is the definition of symmetric relation. Correct? Symmetric relation means for every x, for every y, if x is related to y, then y is related to x. Remember this, you can write like this. This r a comma b, you can also write like this, a r b. So this is all, both are correct. So you can see that this statement, if you notice what this statement is saying, this statement is saying that for every x, for every y, okay, if x is related to y, then y is related to x. This is the definition of symmetric relation. This is the definition of symmetric relation. This is the definition of symmetric relation. Can I say that? Can I say is it valid? Like, can I say every relation is symmetric? Is it valid? Valid means always true. So remember what valid means. Valid means always true. Valid means always true. Can I say it is valid? Like, can I say every relation is symmetric? Can I say that every relation is symmetric? Can I say? So no, definitely it is not valid. Okay, because every relation is not symmetric, because valid means always true. Can I say being symmetric is always true for a relation, for any relation? R can be any relation. For any relation being symmetric, is it always true? The answer is no. Can I say it is satisfiable? Satisfiable means sometimes true. Satisfiable means sometimes true. Yes, it is satisfiable. Some relation is symmetric. Some relation is symmetric. Okay, so definitely some relation is symmetric and its negation is also satisfiable. So B is the answer. Okay, so very simple that this is invalid. Remember, this is invalid, but this is satisfiable. Its negation is also satisfiable. Negation means it is not symmetric. So being not symmetric is also satisfiable. I hope this point is clear. Tell me, did you understand this question? Let me do more analysis. So this statement is given to you. Let's call this statement x. So for all x, for all y. And this statement is saying that for rxy implies ryx. Let's do some more analysis. So you can easily see that. Can you give me a co-model for this? For this S, can you give me a co-model? Give a co-model. Can you give me a co-model? Tell me. Can you give me a co-model for this S? Definitely, very easily I can give you a co-model. For example, you can take this domain. It is not very hard. You can easily give a co-model. Like, I can take this domain like 1, 2. I can take this domain. And let me assume that R1, 2 is true. Okay, this is true. And everything remaining is false. Everything remaining is false. Let's assume R1, 1 is also true and the everything remaining is false. Let's assume R2, false. Okay, and let's assume that R2, false. Now you can easily see that this will work as a co-model. Why this will work as a co-model? This is going to work as a co-model because this is saying that for every x, for every y, this should be true. Okay, for every x, for every y, this should be true. Now you can easily see that this is now this S is in this interpretation, this S will be false. And what will be the counter example? What is going to be the counter example? Which pair is going to be the counter example? Like, consider this pair will be counter example 1, 2. This 1, 2 pair will be the counter example, because for this pair what will happen? Look at this pair. For this pair this will be true for 1, 2. Okay, this will be counter example. Why? Because this will be true. Okay, this will be false. So this entire thing will be false. You can note this will be true, this will be false. So definitely I can say that this S is a false. So this is a co-model. Is this understood? So you can easily say that this is a co-model. Now let's see the can you give a model for this? Can you give a model for this? Yes, I can easily give you a model for this if I make all of them true. Okay, like for example, I can easily give you a model for this. Like what I do? Yeah, this is also model. I can make it false, no problem. This is also a model. In this, you can easily check it out. In this, S will be true. So this is a model. What I'm doing? I'm making S2 to R2 to false and the remaining are true. You can easily see that this is also model because because in this you can notice R is symmetric. Your relation is symmetric. In this relation is symmetric, and you can see in this relation not symmetric. R is not symmetric. Okay, R is not symmetric. Clear? Is this point clear to everyone? Please tell me. So here you can see R is not symmetric. So this is a co-model, and here you can notice R is symmetric. So definitely satisfiable. So definitely this is satisfiable. But and what is the negation of being symmetric? So this S is, remember, please understand that this is nothing but definition of symmetric. This is being symmetric. This is the definition of symmetric. So what is the negation of symmetric? This is the definition of symmetric. Can I say negation of symmetric is asymmetric? Can I say negation of symmetric? This is a simple question I'm asking. What is negation of being symmetric? Can I say negation of symmetric is asymmetric? If something is not symmetric, then is that same as if something is not symmetric? Simple question I'm asking. If something is not symmetric is same as, if something is not symmetric, it's same as, can I say asymmetric? Can I say antisymmetric? Can I say which of them? Which of them? Neither this nor this. Okay, so if something is not symmetric, it does not mean it is asymmetric. Okay, also it does not mean that it is antisymmetric. If something is not symmetric, okay, then it does not mean that it is antisymmetric. It does not mean asymmetric. Not symmetric means no symmetric. Is this clear? Sumant, you can check out our set theory course. In the relation, we have already seen this on the goclass website. In the discrete mathematics course, you can check it out. You can study the relation chapter. There we have already seen this, that not symmetric does not mean asymmetric. It does not mean antisymmetric. Not symmetric is not symmetric. Okay. So remember this. This is the simple point that I want to tell you. So again, you can notice this is definition of symmetric, and being for a relation being symmetric is for a relation R being symmetric, that is valid but not that is satisfiable but not valid. Being symmetric is possible. Possible means satisfiable. Okay, so that is satisfiable but not valid. It is not always true that every relation is symmetric for any random relation. So for this question, remember, the answer will be option B, that it is satisfiable, its negation is also satisfiable. So very simple question. Now let's see this question. Tell me the answer. What the question is saying. First order logic expression is given to you. This expression for all x, there exists y, r x y. Okay, so this statement is given to you. Assume non-empty logical domain. Which of the following sentences are implied by f? Which of the following sentences are implied by f? So you can easily see, first of all, let's see what is this. Let's solve it. If you solve it, then this is negation of quantifier. So this negation you can take inside. If you take this negation inside, then it will become for all x. This existential quantifier will become universal. This universal quantifier will become existential quantifier. So this will become existential quantifier y. And this negation will go inside. Negation and negation, they will cancel. So basically it will become rxy. For all x, there exists y, rxy. So definitely they are these are basically same. The given expression f, that is basically equivalent to the fourth. Okay, so fourth will definitely be the answer. Which of the following is implied? So fourth will definitely be the answer. So this is not correct. This is not correct. So tell me, from in the GATE exam, only which option will you check? In the GATE exam, which option will you check? Of course, in the GATE exam, only you have to check for the option 1. This is the only option you have to check, because fourth is definitely equivalent. So let me check this option 1. The remaining options you can check. So this statement is given, f is for all x there exists y pxy. For everyone there is someone such that rxy, okay, whatever, rxy. Now what this option 1 is saying, this option 1 is saying that there exists y, there exists x such that rxy. Okay, so this is the statement. Let's see, is this valid or not? We need to check, does it imply this? Okay, let's check it out. So first of all, you can notice what this means. This means that for everyone, let me assume ABC, for everyone there is someone, right? For everyone there is someone such that, like, for everyone there is someone, for this is this. Or I can say, for example, for everyone there is someone. Let's assume for this is this. For everyone there is someone. So let me assume for everyone there is someone. Okay. So now you can notice for everyone there is someone means are A, B true? For A there is B, for B there is C, and you can notice for C there is A. So all of them are true. Now you tell me, can you make it false? What this is saying? This is saying that there is some y, such that there is some x, there is some y, like, okay, some y is there and some x is there such that rxy. So you tell me, yes, of course you can easily see that, you can easily, if this is true, then definitely it will be true, because you can easily see there is some y, you can take this y, there is some x, okay, some x you can take, there is some x, you can easily see that c, I can say what I'm saying. So there is some y, there is some x, such that you can easily see that AB is true. So this is definitely true. So this is actually valid. Are you getting my point? So this is actually valid. Let me tell you what I'm trying to say. It is very simple that we are saying that for everyone there is some y. For everyone there is someone, basically. Okay, so for whatever you take, like A, B, C, whatever you take, there is some y. For everyone there will be some y. For example, for this there is some y. Now remember, for the remaining also there will be there, but this is enough. Or now automatically for everyone there is some y, okay, such that RAC is true. Now this is enough. This is enough to make it true. This is enough to make it true, because now you can easily see there is some y. What you can do, you can take this C as that. Okay, you can take this C, you can take this C, and you can take this A. Now you can notice that this AC will be true. So clearly this is a valid. This is always valid. Okay, so very simple. Now let me tell you a few things. So this is simple point that, remember, for every variable the domain is always same, as I told you. So for every variable domain is always same. So that is the reason you can see for all x, for all y, if you have this type of statement, for all x, for all y, pxy, this is same as for all y, for all x, pxy. So this universal quantifier, if there are two universal quantifier, you can change them. Okay, this is correct. So two universal quantifier, you can change their order. The order does not matter if you have two universal quantifier. Similarly, if you have two existential quantifier, the order does not matter. If you have this, okay, so this will be same as there exists y, there exists x, pxy. Okay, so if you have two existential quantifier, then also order does not matter. Very simple. But remember, these are not equivalent. For all x, there exists y, pxy, there is a universal quantifier, there exists existential quantifier. This is not equivalent. This is not equivalent if you change the order. There exists y, for all x, pxy. They are not equivalent. So you cannot change the order of two different quantifiers. Of course, this is true that if you have for all x, there exists y, for everyone there is someone. See, for everyone there is someone, then definitely for someone there is someone. Do you agree? Are you getting my point? For everyone there is someone. For everyone there is someone. Then can I say for someone there is someone? Yes, of course. Correct. And remember, this is equivalent to there exists y, there exists x, pxy. So you can see this will imply this. This is your option. This is your option. This is your 1. If you notice, this is your 1 and this is your F. So F implies 1 is valid. This is a valid. Is this understood? Dangerous Khiladi, is this understood? Tell me. Is this understood? Please tell me. Let me know. So, very simple. So, you can easily see that for all x, there exists y, pxy. This implies for everyone there is someone. So, I can say for someone there is someone. For everyone there is someone. So, automatically for someone there is someone. Now, this is same as this. Okay. So, these two are basically same. Now, that is the reason you can see that F implies I is a valid. The remaining options you can try. I am not going to do. The remaining options you will try, but the answer will be option B. I give you the remaining options as a homework. Please do them. The remaining options, okay, try them. The remaining two options are your homework. Is this clear? Ratul, Sumant? See, all the homework that I am giving you, please do all these things. These are for your benefit. Getting the answer is not enough in the GATE exam. See, in the GATE exam, you can do. In the GATE exam, you don't have to do the options second and third. In the GATE exam, you don't have to do this in the GATE exam. But during preparation, you should do. Okay. So during preparation, solving the question is not enough. Getting the answer is not enough. You should do complete analysis. Okay. This is the motto of Go classes also. So this you should always do. Solving question, getting answer is not enough. Complete analysis you should do. So this point. So remember this point. Getting answer not enough. Okay. Complete analysis is mandatory. So that is the reason I am giving you this as a homework. You can try this. The remaining two options I have done, you can do this. If you have any doubt, you can watch the Go classes discrete mathematics course. Now let's see this one. This question you can easily solve from our table or you can prove it. So tell me, from the table, can you solve this question? Sumant, Dangerous Khiladi, Ratul, tell me the answer for this one. Sukesh, tell me the answer. So, which of the following are valid or not? The question is very simple. This is a GATE 1992 question. Again, you can easily see that universal quantifier from expanded to compact. Can I go? Can I go from expanded to compact? So, this table you already know that for all there exist. And there is conjunction, there is disjunction, there is implication. This table we already have that this is a, this table is like this. Now, okay, so now you tell me. So you can see this universal quantifier in the case of OR, it is going from expanded to compact. In the case of OR, it is going from expanded to compact. So definitely this will be valid. So this option A, this is definitely valid. Okay, because we are going from expanded to compact in the case of OR. You can notice this universal quantifier in the case of OR, it is going from expanded to compact. So this is definitely valid. What about the next? Existential quantifier in case of AND. Existential quantifier in case of AND, it is going from compact to expanded. Okay. This existential quantifier in the case of AND, it will go from compact to expanded. So this is definitely not valid. Option B is not valid. What about the next? The next, you can easily see that this will be not valid. Option C is also not valid. Okay, what about the next? What about D? Let's try this D. This D is actually very simple. You can see that there exists X. This is saying Px or Qx. This is your LHS. Now, you can simplify this. This will become what you do. Here, this negation is applied on the universal quantifier. So, the negation of universal quantifier will be existential quantifier. Negation of Px or there exists quantifier Qx. So, the question is asking, does it imply this? Does this imply this? Okay, this we have to check. The table will not help you, right? Correct? Yes or no? The table will not help you. Agree or not? Because in this question, the table is not going to help you because this is not a distribution property. Here you have Px, here you have negation Px. So the table is not going to help you. Do you agree that in this question the table will not help you? So whenever table does not help you, then definitely you have to apply the proof, the formal proof you have to apply. So let's solve this question. This is your existential quantifier px or qx implies existential quantifier negation px or existential quantifier qx. Let's see this. Can we solve this question? So let's see whether it is valid or not. Let's check. Is this valid or not? Okay. So let's see this quickly, whether this will be true or false. So again, very simple method, extremely simple method. You don't have to do anything. The method, the formal method is very simple, that you have some domain. This is the domain. Now in this domain, let's assume, let's assume this is A. Let's assume this is B. Can you do this? Can you make A true and B false? Can you do this? A true, B false. Can we do this? Is this possible? Simple question I am asking. Is this possible? Can you do this? A true, B false. So first of all, to make A true, what I can do? Just simple question. To make A true, what I can do? To make A true, if you want to make this A true, then for some element, this P or Q must be true. For some element, either P or Q. For some element, like for this element, so let's assume P must be true for this element. So now you can notice A is true. This is done. Okay, so we have created this A true, we have done. This we are done with this. Now can you make B false? If you want to make this B false, this is OR, remember there is OR here, disjunction. So if you want to make B false, then definitely you have to make it false. Can you make it false? Of course I can make it false. If you want to make it false, this is existential quantifier Qx. If you want to make it false, then for every element in the domain, Q must be false. For every element in the domain, this Q must be false. For every element, this Q must be false. Now, can you make it false? Can you make it false? Can you make it false? Now you can see that, of course I can make it false. If you want to make it false, then what you have to do? For every element, this must be false. For every element, P must be true. Okay, if you want to make it false, remember, this you want to make it false. Look at this. This you want to make it false, then for every element, this must be false. So for every element, P must be true. For every element, this P must be true. So yes, I can make for every element P must be true. So yes, I can do this. For every element, P must be true. So yes, this is possible. Yes, this is possible. So this is possible. Answer is yes, this is possible. And if this is possible, then D is invalid. Then D will be invalid. Isn't it? Okay. Is this clear? Tell me. Intuitive proof. Can you apply the intuitive proof? Again, the same example. This is the bike. Let's assume this is the bike and this is the car. Let me assume this is bike and this is car. So tell me, in this city, there are three people, A, B, C. These are the three people in this city. Now, what this statement is saying, this is saying that, look at this. This is saying that there is someone who has bike or car. There is someone, let me assume this is the person who has bike or car. Let me assume he has car. Okay, he has car. Okay, so let me assume this person. These are the people. These are the people. Okay, so let's assume B has car. Now you can notice this is true because this is saying that someone has bike or car. So this is fine. Now what this is saying, this is saying someone has car. Okay, it is saying that. So what I can do, I can assume that this has bike. I can assume he has bike. I can assume this. What I can do, I can assume that he has bike. This B, this has bike. Because remember, there is someone who has bike or car. In this city, very simple. Look at this. In this city, there is someone. Let's assume that person is B. He has bike or car. So let me assume he has bike. Now you can notice it is not mandatory that someone has car. So you can say this is false because no one has car. Okay, there is no one who has car. And you can notice this can be false. see, this can be false, right? This can be false if everyone has bike. If everyone has bike, then what will happen? Then this will be false if everyone has bike. So you can clearly see that if everyone has bike, then this will be false. If no one has car, then this will be false. So clearly this will be invalid. So this is clearly invalid. So this is your another intuitive proof, but I think this formal proof will always help you. Tell me, which proof is your favorite now? We have seen many formal proof. A lot of formal proof we have seen. Did you notice that formal proof will always give you correct answer whatever variation they create? They create. They can create any variation they want. Okay, they can mix universal quantifier, existential quantifier. They can mix operators. Whatever they do, they can do. This formal proof will always help you. Okay, this formal proof is always going to give you the correct answer. A lot of formal proof we have done. So anyway, so this statement you can notice this is invalid. So finally your answer will be only option A. This is the only answer, option A. Let's try this. So what this question is saying, look at this. This question is saying that alpha and beta are the first order formula which access their only free variable. What this means? Does 4 all x affect this or not? Tell me what this means. Like if let me assume, tell me simple question I'm asking. If alpha has free variable x, if this alpha has free variable x, then does 4 all affect it? Tell me. Then does 4 all x or existential x affect alpha? Tell me. Basically, I want to say that if I write this 4 all x alpha, will it be proposition or not? If alpha has free variable x, the only free variable x is there. So you tell me now, in this situation, the answer will be yes. Because remember, if alpha has free variable x, then definitely, if the only free variable is x, then definitely what will happen? This 4 all x, if alpha has only free variable, this is the only free variable, then in this situation, remember 4 all x alpha will be a proposition. Okay, right? This will be a proposition, and there exists x alpha will also be a proposition. This also will be a proposition. This also will be a proposition. Like, this is like some students are confused. See. Look at this px. X is even. Here x is free or not? Consider this as alpha. Okay, here x is even or not? Here x is free or not? Tell me. In this x is free or not? Can I say x is free? Can I say here x is free? Look at this px. Can I say x is free? The answer is yes. Yes answer. Yes or no? So this is your alpha. The question is saying that this is your alpha. So you can assume that alpha is px. Are you getting my point? See, in the exam, if they give you like this, you can easily do the question. I know many students, they can easily do the question. Many students are comfortable with this. But students who do not understand free variable, bounded variable, they are not comfortable with this. But actually they are basically the same here. Because alpha, in the alpha you have x is free variable. Is this point clear? Sumant, dangerous khiladi, tell me, is this point clear? See, very simple question. In the exam, if they give you like this, if they give you px, x is something, then you can clearly see here x is free. You can clearly see that x is here free variable. X is free variable, x is not bounded variable. Now if I write like this, for all x px, if I write there exists x px, now students are very comfortable with this. Yes or no? So here the students are extremely comfortable. In these two, these will be proposition, these will be proposition. Students are very comfortable. Okay, so these two are basically proposition. But the same thing he's saying, he's just saying that this x is free variable. He's just saying that this px is basically alpha. In the question, he is saying that this px is basically alpha, because in the alpha you have free variable. Okay, in the alpha you have free variable. So this is basically same as what? This is basically same as 4 all x px. right? Yes or no? This is basically same as this, and this is basically same as there exists x px. Is this point clear? Now the problem will happen when? Now the problem will happen when x has no free variable. See, if alpha has no free variable x, if alpha has no free x, if alpha has no free variable x, now you tell me, if this alpha has no free variable x, now you tell me, what about this? For all x alpha, what is this and what is there exist as x alpha? What are these? Please tell me quickly. This we have already seen in the revision, in our revision lecture. The concept of free variable, the concept of bounded variable, all these concepts we have seen in the revision. You can check it out on the Go Classes YouTube channel. You can find out first order logic revision lecture. In that revision, we have already seen all these concepts, all these things we have already seen. And if you want to study the same concept, what is free variable, what is bounded variable, all the variations, okay, mixing of these. So if you want to understand this completely, then you can watch Go Classes Discrete Mathematics course. Everything is taught with variations, with questions, a lot of exercise we have done. Okay, so you tell me about this one. If x has no free variable, if there is no free variable x, if there is no free x, then this is equivalent to alpha and this is also equivalent to alpha. Take example. Take example. Why are you so worried? Okay, why are you so underconfident? See, take some example. X has no free variable. So you can take this example that, for example, 2 plus 2 equal to 5. Take this example. Can you notice there is no free x? Can you notice there is no free x? Can you notice there is no free x? Yes or no? There is no free x. So you can easily see that if I ask you for all x alpha, that simply means for all x 2 plus 2 equal to 5. It will only depend on alpha, right? Yes or no? The answer will only depend on alpha. I can say the answer will only depend on alpha. Is this clear? The answer is only going to depend on alpha. So this will be same as there exists x 2 plus 2 equal to 5. The answer will only depend on alpha. That is false. So this is what I am saying. I am just saying that if x has no free x in this alpha, if there is no free x, okay, no free x, if there is no free x, then what will happen? Then it simply means that for all x alpha will be alpha and there exists. So in this situation I can say universal quantifier. In this situation, for all x does not affect for all x or there exists x does not affect what? Does not affect alpha. Yes or no? Does not affect alpha. Clear or not? Okay, so very simple. So remember, final conclusion is that in this question, don't be confused. Those students are confused in this question who don't understand what is free variable, what is bounded variable, all the variations, what are the possibilities, what are the questions, what are the tricky questions. Okay, so basically if you clearly understand these concepts, then you will not be confused. Now you can easily see, if you understood what explanation I gave you, if you understood that, then what you can do, this alpha you can consider as px and this beta you can consider as qx, so that you are not confused, so that you can solve this question peacefully. Okay, so what I'm saying that alpha is nothing but px and beta is nothing but qx. Now let's see. So now this table you already know. For all x there exist for all there exist and or implication, only these things are needed for this question, only these things we need. Okay, so this table you can very easily see that this is the table. For all, in case of conjunction, will go both side. Here this side, here this side, here both sides, here this side and here this side. Okay, so like this you can check it out. Now let me so tell me the answer for this one. What about option A? Option A you can solve using the table very easily. You can see that universal quantifier in case of implication will go from compact to expanded. Okay, is this clear? The universal quantifier in the case of implication, it will go from compact to expanded. From compact we will go to expanded. So you can notice from compact we will go to expanded. So this is definitely invalid, right? The question is asking which is valid. So this is definitely invalid. The other direction will be true. So if you have this direction will be true. it will be valid. This direction will be valid. So this option A, this is definitely invalid. Option B, the table will not help you. Do you agree? Correct? Yes or no, Sumant? The option B, the table will not help you. Option C, table will not help you. Okay, but option D, table will help you. This is valid. This is definitely valid. Option D is basically valid because from compact you are going to expanded. Okay, from the compact side you can go to expanded side. So this is definitely valid. Now let's check option B. So let me try option B. Let's see the explanation of option B. What this option B is saying? This is saying that for all x alpha implies there exists x alpha. So this is for all x px. You tell me, for all x px, can I say there exists x px and qx? Simple question. Simple question. Intuitively, let's think. Let me think intuitively. Let me think intuitively. Let's assume this is mobile. This is mobile. Okay. Let me think this is mobile. So let me assume that this is a car. And this is your mobile. If everyone has mobile, then can I say someone has car and okay, let me actually assume that this is this qx. This q is, let me assume, Mars. Okay, whatever, like you can do something which no one has. You can do something which no one has. Can I say that something which no one has? Is there anything which no one has? Unicorn. You can assume some unicorn. Okay, so magic pencil or whatever, like magic pencil or magic wand, whatever. So you can see that. Tell me, if everyone has mobile, then can I say there is someone who has mobile and unicorn? Tell me. Intuitive proof. Very intuitive proof. Tell me, if everyone has mobile, can I say someone has mobile and unicorn? Definitely, the very intuitively this is invalid, right? Intuition is saying that this is invalid. Yes or no? Intuition is telling you that this is invalid. Correct? Or agree or not? Okay. So very simple, that this is definitely invalid. Intuitive proof. If everyone has mobile, almost nowadays everyone has mobile, it does not mean that there is someone who has mobile and unicorn. So definitely I can say this is invalid. The same thing you can prove with our formal method. Can you try our formal method? Can you try our formal method? Tell me. So let's assume some domain is there, A, B, C, and so on. Now, this is your A. This is your, or I can assume that this is your Z, and this is your Y. Is this possible that Y is true, Z is false? Is this possible? This thing. Is this thing possible? Is this possible? So you can see, can I make this Y true? Yes, I can make this Y true. For everyone, I can make P true. For everyone, I can make P true. For everyone, I can make this P true. So yes, this Y true I did. Can I make this Z false? Can I make this Z false? So yes, I can make this Z false. What I will do? For everyone, this Q I will make false. For everyone, this Q I can make false. For everyone, this Q I can make false. So you can notice this is false. So is this possible? The answer is yes. This is possible. So this B will be invalid. So okay, so this B will be invalid. This B is going to be invalid. Very simple, right? Isn't it? If I do this OR, a variation I am asking, if I do this OR, now you tell me, this is a variation. A simple variation I am asking, you tell me now. A simple variation. For all x px, can I say, if everyone has px, means if everyone has mobile, then can I say someone has mobile or unicorn? Definitely this will be valid, right? This is going to be valid. Okay, this will be valid because for everyone P is true. If for everyone P is true, then definitely for someone this will definitely be true. So you can easily see that this will be valid. Okay, is this clear? So very simple, you can do it. Now, so for this question, you can clearly see this is invalid. Okay, let's see the next. What about the option C? Option C is saying that for all x alpha or beta, then can I say that there exists X alpha implies for all X alpha? Okay, so option C, what this option C is saying? This option C is saying that for all X alpha means for all X Px, does it imply for all X Px, sorry, Px or Qx? For all X Px or Qx? For all X Px or Qx, does it imply there exists X Px implies for all X Px? Okay, so there exists X Px implies for all X Px. Okay, so let's check it out. So tell me again, in this question, you can again easily see intuitively. Can you solve it? Can you tell me? Can you solve it intuitively? Intuitively, can you solve? So you can notice for everyone P is P or Q. Everyone has P or Q. Everyone has P or Q. First of all, you can solve this actually. Before solving this question, this implication you can change. So you can do like this. This for all X Px or Qx implies, in this side what you can do, you can write it negation of this or this. Okay, negation of this or this. So what you can do this negation of there exists X Px or for all X Px. Okay, this will be what? This will be for all X negation Px or for all X Px. Okay, so this is saying that for all X negation Px or for all X Px. So tell me, if everyone has P or Q, then can I say either everyone has P or no one has P? Can I say? Can I say if everyone has P or Q? If everyone has P or Q, then can I say this? Simple thing, simple question. Is this valid? Simple question is I am asking, can I say this is valid? This is definitely invalid, right? This is definitely invalid. Why this is invalid? What is the reason this is invalid? Okay, so forget about everything else. Forget about these things. What is the reason this is invalid? This is invalid because if everyone has P or Q, for example, either bike or car. So let's assume in this city there are three people. In this city there are three people. Now you can notice maybe this person has bike, maybe this person has car, maybe this person has bike and car. Now you can notice that this is true. This is true because everyone has bike or car. Is this true? This is false because everyone does not have bike. Okay, because this is false because not everyone has bike. It is also false because someone has bike. So you can notice this is false because not everyone has bike, and this is false because someone has bike. So definitely this C is what? This C is invalid. Is this clear? Please tell me. Let me know. So very this intuitively you can do this question. You can solve intuitively because very simple. You are saying that everyone has P or Q. Everyone has bike or car. Whatever person you take, they have at least one vehicle. Either they have bike or they have car or they have both. Okay. So does it mean that everyone has bike? No. Does it mean that everyone has? Does it mean that everyone has bike? No. Does it mean no one has bike? No. Okay. So definitely you can see this is a invalid. So this option C, this is also invalid. So this is your question. This is another gate question. So we have done this question also. The answer will be option D. That is the only option that is valid.